Okay, so I am an assistant professor of sport analytics, which is a really ridiculous job. To explain what that is, when I was little, the first thing I wanted to be was a baseball player. And that's kind of a ridiculous job because you're playing a game for a living, making money. So that didn't work out. I wasn't sufficiently athletic, so I became a data scientist working for baseball teams, which is like a layer more ridiculous than being a baseball player because I'm not playing baseball. I'm doing math to help tell people how to play baseball better. And now I've achieved just a fully ridiculous job because I don't do math to tell players how to get better. I teach students how to do math so that students can tell players how to get better. So I realized that this TAMIDS seminar series is for data science and not necessarily for sports. So I want to do a brief introduction of like what is sport analytics. And this is how I envision sport analytics in my head. So professional sports teams have access to all sorts of data, and they have to understand how to interpret the data in order to make decisions, make predictions about what players are going to be good. And I like to think of it as this is what gets me passionate about sport analytics and statistics. Is I feel like I'm looking into this like crystal ball that's swirling with data and trying to come up with answers that are going to help teams win more games. So as for how I got into this, I feel like where this discipline came from. We all of us working in sport analytics today have this book to think for working in sport analytics, and that was Moneyball, which was about the 2002 Oakland Athletics. That doesn't need an introduction. It spawned this whole genre of books about teams using data to win more baseball games. There was the extra 2% about the Rays, the Tampa Bay Rays in 2008, Big Data Baseball about the Pittsburgh Pirates in 2013, and then Astro Ball about the Astros in 2017. Incidentally, the 2017 Astros, I was on the losing end of that World Series because I was with the Dodgers at the time. When I entered baseball, this was the state of R&D staffs in baseball. As a quick aside, my source for this slide is Reddit. Not my proudest moment as an academic, but I was working for the Dodgers, who this source estimated in 2018 we had like 20 analysts in R&D. We were along with the Yankees, we were one of the biggest staffs in baseball. And since then, that has only continued to grow, where a recent estimate by someone on Reddit in 2025 had like the Rays, the Phillies, over 40 R&D staff. So the question is like, what are all these people doing who are doing research and development analytics for pro baseball teams? I've got one artifact from when I was working at the Dodgers. This was something that we put together for a career fair when I was working at the Dodgers. We were trying to explain what it is that R&D does. If you were to apply for one of these jobs, what might you expect to do? And so there's sort of three areas of application. There's player evaluation, which is trying to measure how good is this player. If we add this player to our team, how many more games are we going to win? There's player development, which is instead of like adding good players to our team, can we make the players that are already on our team better? And then lastly, in-game strategy. Can we make better decisions in the game to win more games with the players that we have? So those are the three general areas of application that we worked on. And what I have for you today are three examples of public projects I've done since I left the industry, but sort of illustrate the kind of projects that R&D staffs will work on. So I've got three puzzles I'm going to share with you that cover three different aspects of baseball. So the first one is going to be about base running. The second one is going to be about hitting, and the third one is going to be about pitching. But before we get into the first one, I'll pause here. What questions do you have about sport analytics generally?
So how does it apply to other sports and baseball?
So baseball is like sort of the leading sport for this because it is so well described by the data. If you look at a box score, you can really visualize what's happening in the sport. Whereas, June and I were talking about this earlier this morning. Soccer is at the opposite end of the spectrum, so it still applies. It's just that what we're able to describe with the data is a much smaller percentage of what's going on in the game. So it still gets used, but something I was reflecting on as recently as last week is it's a lot harder when you're working with like a soccer team or frankly a basketball team. It's a lot harder to get buy-in from coaches to actually make decisions based on the player evaluations or the in-game strategy recommendations that you have. And maybe that's natural. Maybe it should be more difficult because when you build these models for soccer, you're missing more of the game. There's a bigger gap between what you're doing and what's actually going on the field. So it still applies to the other sports. It's just that the gap I think is bigger between what our models look like and what's going on in the. So this first project, it's a base running project. It's a collaboration with some OR folks. Siva Ramani. This is the first collaborator for whom I've just not been able to find a picture for him. He's pretty good about staying offline. He's a postdoc in OR at Rice. Jacob Hahn was an undergrad at Rice studying statistics and sport analytics. He's with the Chicago Cubs now in baseball operations. And Andrew Schaefer is an OR, that's an operations research professor at Rice. And this project was motivated by a rule change that happened going into the 2023 season in Major League Baseball, where among many rule changes to make the game more exciting, they limited the pitcher to 3 pickoff attempts. A pickoff attempt is the primary deterrent that a pitcher has against base stealing in baseball. So I'm going to pull up a video to illustrate this. So here's like a Jonathan was mentioning Chicago earlier. Here's a meaningless game in May between the Chicago Cubs and the hapless Chicago Cubs.
Well, the only problem is now there's 2 throws over there, and Tucker's going to get a much bigger lead.
So the pitcher Sean Burke.
My sense was that he was thinking about stealing on that last pitch.
And Steve Stone, the commentator for the White Sox, mentioned that now there's going to be a big
Tucker looks for a jump, and he had him if he threw over, and Sean Burke was told to step off.
Yeah, there's a brand new
that
philosophy.
Second step
Don't
off
look at
is
the guy
the
at
second
first base,
attempt.
because if you did,
so now he only gets
he
one
would be
more
inning over.
Steps, and if he throws it over, then either the runner is out or the runner gets the next base for free.
Tucker takes off again before the pitch is thrown, and Carroll has no chance to throw him out.
So to break down what happened there, because
I'm not sure exactly when this has become a thing where you don't look at the runner, but as you can see, Tucker
sort of knows it's very low probability that the pitcher is going to throw.
And I don't think anybody
he gets such a massive jump. I don't know if you saw this, but he paused after he got the jump because he couldn't believe what the incredible jump was he got on that pitcher. Sorry, I was talking over it, but Stone at the end of that video clip says, "I don't think anyone in the world could have thrown that on that play." So the point I'm trying to illustrate is that this 3 pickoff attempt limit creates an interesting cat and mouse game between the pitcher and the runner. Because once the pitcher has thrown over 2 times, as a runner, the pitcher is highly disincentivized from throwing a pickoff. If first base is over here, I'm the runner. I know the pitcher is really disincentivized from trying to pick me off, because if I get back safely, then I get the next base for free, especially the stolen base. So I should push my lead a little bit further. That gives me an advantage if I attempt a stolen base, and maybe I can bait the pitcher into throwing back over to first. But the question that we're trying to answer is can we quantify this? Can we quantify how much you should extend your lead after the first pickoff attempt, after the second pickoff attempt? Because after 2 pickoff attempts, it's obvious I should extend my lead, but the same is true after 1 pickoff attempt, because I'm getting closer to that 3 pickoff attempt limit. So for the most part, the data that we're using here are publicly available. We know like every event that happens in a Major League Baseball game. The one thing that was proprietary was lead distance. So MLB has player tracking data, which is getting the position of all of the players on the field throughout the entire play. And what that allows us to get is the a lead distance for every player, which we measure as the distance from, if I'm the runner, the distance from my center of mass to the nearest edge of first base. That's how far my lead is off the base. And so this lead distance is our primary variable of interest here. How do we choose lead distance to optimize run score? Please interrupt.
Why the center of mass? Because you just have to touch the first base, right? You don't. So why not your reach instead of center of mass?
The center of mass is what MLB was going to give us. Drew, that's a good question. MLB is starting to do pose tracking, where we actually know like where the hand is, which will be an interesting opportunity for future work, where the most of that work will be talking to MLB's lawyers about why you should donate data to academics. What other questions do you have about the problem setup here?
Why is this such a challenging problem though? Because I would think statistically it would be a simple problem of after each attempt you just increase the determinable amounts of like return on an investment there is that after each throw you're just increasing by a static amount of probability.
Not necessarily static. I guess what makes this challenging is that based on the state that I'm in, based on the state the game is in, the ball strike count, the number of prior disengagements, there's some the lead distance I take is going to affect where we transition to the next state. And so if I know the values of those states, like if I know the value of having 2 disengagements, then I know what to do when I have 1 prior disengagement. But until we solve for the optimal action in every state, we don't know what the value is of all of the other states. I just saw this question. Uh-oh.
A question from the audience.
And I just lost.
Also, in today's game, Drew, the worst thing that could happen is getting thrown out on a base. Basically, like everybody agrees, that's awful. So you can't take an interminable lead knowing that you could get picked off.
Okay, sorry about that. I see the question and I will get to the question in a moment. Sorry.
You hide the floating control stick.
And now, okay. Sorry.
You could.
From a like operations research perspective, this is an interesting question because the model, it's not obvious how you solve for the optimal policy for the picture. I'll get into in a moment. I saw that there was a question on the Zoom about like navigating issues with getting access to proprietary data. And the question was like advice on that. It's difficult. The thing that worked for me is having like personal relationships, having worked in industry. When people work for the league, know who you are, they feel more trusting and more willing to give you the data. And I realize that's generally not actionable advice for academic researchers, but it's the truth as far as what moved the needle on getting access to data. Now, there are a lot of interesting publicly available data sets in sports, which I can touch on. We have Q&A.
Having really good students who now work for those teams and leagues also helps too. Right?
It builds on itself, right? Hopefully those students get into positions where they're deciding whether or not to give me data. So in order to answer this question, it's a 2-step process. The first thing that we need to understand is what's the relationship between lead distance and outcomes for the runner. So that's what we start. We need to know if I extend my lead by 1 foot, how does that change my probability of getting picked off? How does that change my probability of stealing a base? So the approach that we take is we use linear mixed effects models. So in particular, we're predicting whether the pitcher is going to attempt to pick off, whether I'm going to be out on a pickoff, whether I'm going to attempt a steal, and whether I'll be safe on a steal. And so these are logistic regression models where we have fixed effects and we have random effects. We have fixed effects for lead distance, the number of balls and strikes, and we have random effects for fixed effects also for the runner's sprint speed, the catcher's arm strength, and then random effects for the player's ball, random effect for the pitcher, for the batter, for the catcher. And when we put these models, we gain this understanding of how does lead distance change our success probability. So this right here is our probability of a pickoff attempt as a function of lead distance. So it's really, really low until you get past 12 feet, and then it starts to increase a bit more. In particular, the gray curve is 2022 before the pickoff limit, and that's why the rate is higher in 2022, because pitchers weren't disincentivized from attempting more pickoffs. And then the solid blue curve is before there were any disengagements. Disengagement is the formal term for a pickoff attempt. This is the probability in 2023. After the first disengagement, the probability goes down, and after 2 disengagements, the probability is really, really low of a pitcher attempting a pickoff, even if the runner has a massive lead, because of that dynamic that we talked about, where the pitcher really has to get the batter out in order to justify that pickoff attempt. So there's pickoff attempts, and then there's also the flip side of a stolen base. So if you attempt a stolen base, for any given lead distance, here's what we model as your probability of successfully reaching second base. So here, the gray curve is the median runner in 2022, and the solid blue curve is the median runner in 2023. The reason for that big gap is that in addition to the change in the pickoff rule, there was also like a pitch timer, and they also made the bases a little bit bigger. So there were a few different rules that made base stealing easier in 2023 versus 2022. The dotted line up here is like a 90th percentile runner. The dashed line is a 10th percentile runner. So even like a 10th percentile runner in 2023 was more successful when attempting steals than a median base runner in 2022. I'll pause here for questions.
What was the metric you guys used to calculate the catcher arm strength? Like what kind of used for that?
So Baseball Savant reports catcher arm strength measured in miles per hour on the not on a pitch by pitch level, but on the season level. So for example, like Martin Maldonado, they have a measure of how hard he throws the ball, and in detail, they take every stolen base attempt against Maldonado, and they look at it's something like the average of the top 50%, like a trimmed mean for each player. Now these data are publicly available on Baseball Savant. What else?
I know it's pitcher arm strength isn't there, but I've seen pitchers throw to catch the attempts off first, right? I mean, I'm sorry, catcher arm strength isn't one of those metrics.
Yeah, we don't. That's a good point. In the model that we set up, we don't allow for back picks as a probability. A back pick is when the pitcher does not attempt to pick off, but the catcher after receiving the pitch will throw the ball behind the runner in an attempt. And we don't allow that as well. We do have random effects for the pitcher's pickoff ability, which, sorry, I neglected to mention it here. We've got 3 curves here. And here, the dotted line is like a 90th percentile pitcher in terms of pickoff ability. Whereas the solid line is the median pitcher, the dashed line is a 10th percentile pitcher. So we see that's a very like right skewed distribution of pitcher talent, where some pitchers are really, really good at attempting pickoffs, but the average pitcher and the worst pitcher are pretty similar. Okay, so we gained this understanding of the relationship between lead distance and runner outcomes. And once we have that, now we need to find like the optimal lead distance policy. And this is where it gets interesting from an operations research perspective. We have two different models for this. I'm going to talk first about the two-player stochastic game, because that's what gets my OR collaborators really excited. So we model this as a sequential game, meaning that first the runner chooses their lead distance, and then the pitcher gets to observe that lead distance before deciding whether they're going to attempt a pickoff or not. So that means that for any given state, the runner is going to be following like a mini-max policy. I'm going to choose the lead distance so that the pitcher is indifferent to attempting a pickoff or not. Because if I choose a lead distance where the pitcher definitely wants to attempt a pickoff, that means that I could have had a greater value with a shorter lead. So for any given state, it's like a mini-max decision for the runner. But in order to solve for the optimal policy, like where is that threshold where the pitcher is indifferent, we have to find the value of all of the states at the same time. So in the paper, we show that we can use value iteration in this setting in order to find the I guess I would call it the equilibrium policy for the runner and the pitcher, where the runner chooses a lead distance and then the pitcher is indifferent to attempting a pickoff or not. That's via an algorithm called value iteration from operations research. Now, I personally think that the single player model is more interesting because I've worked in baseball. And I know that pitchers aren't that smart. So the two-player stochastic game says, if I'm the runner and I assume the pitcher is acting optimally, then what should my lead distance be? But if I were giving advice to a runner, I would not want them to assume the pitcher is going to act optimally. I want them to assume that the pitcher is going to act the way that we've seen pitchers act in the past, because that becomes an exploitable strategy where we can do something better than the game theoretic equilibrium. So in the two-player game, the pitcher has agency and can decide whether to attempt a pickoff. In the single-player game, the pitcher does not have agency, and we assume that the pitcher is a stochastic process who makes pickoff attempts according to the probability that we modeled two slides ago. So when we do that, when we set up the single-player Markov decision process, we can find the optimal lead distance for, and this is standard value iteration for this model. We can find the optimal lead distance for any given state. And that's what we're looking at here. So within this table, we're looking at different counts, where row by row, the number of balls is increasing. And then within block by block, the number of strikes is increasing. And then we're looking at a different number of disengagements in each of the columns. So in order to interpret these numbers, let's just focus on this row right here. It says that at the beginning of a plate appearance, the optimal lead distance is 10 feet, assuming you're an average runner. And then once a pitcher attempts a pickoff, the optimal lead distance is 11.5 feet. So we think that you want to extend your lead by 1.5 feet after that first pickoff attempt. And then after the second disengagement, we think that you should extend your lead by another 2.5 feet, so like a 14-foot lead. That's how we read the results from this table. And if you go down the columns, what you see is that those differences as after each pickoff attempt, they're pretty stable. The difference between each of the values in the first and second columns, it's about 1.5 feet. And the difference between each of the numbers here is about 2.5 feet. So based on this, I wanted to call this like the 20-30 rule, because after the first disengagement, it should be 20 inches, and after the second disengagement, it should be 30 inches. But my collaborator, Jacob Hahn, he has worked with even more baseball players than I have. And so he knows better. He said, no, we call this the 2-foot rule, because it's gotta be simpler than that. So the recommendation that we make based on this research is after each pickoff attempt, you should increase your lead by 2 feet. And so that's how we quantified this like cat and mouse dynamic between the pitcher and And if a team were to do this, we estimate that we would expect them to score 12 more runs over the course of a full season, which may not sound like a lot, but when you consider what teams pay for runs in free agency, this is a $12 million solution right here. But I don't care much for money. That's why I'm an academic now. That's the conclusion of the first project. What questions do we have about choosing a lead distance for a base runner?
I guess when the runner is taking its lead, did you take into account like whether the runner should be like pretty still, like when they're taking the lead, or like what's his name, Jose Caballero, like he like bounces around
and you kind of saw that with Kyle Tucker too,
yeah,
where
on
when
the
the
second
pitcher
one.
started moving, which is when we observed the data, the player was actually moving. That's a really insightful question that shows that you're tracking what we're doing here. And the answer is that in this model, we are making the assumption that the batter is still. So that limits like the application of this model. In particular, we're also assuming that the batter can't the runner, excuse me, the runner can't like stand in a certain spot, but I could be leaning this way, right? So maybe my effective lead distance is a little bit longer, and maybe the pitcher can't see that, which is something else that we could potentially answer with the body pose data that you were talking about. Good question.
Well, I know nothing about baseball, but you were assuming kind of an average player, right? So are there characteristics of the player that could be taken into account to give a conditional recommendation depending on the characteristics of?
Yes, and we have those results in the paper. So I mentioned that we used player random effects as well as the sprint speed and the arm strength in the model. And so we can determine the optimal lead distance for any runner skill and for any like pitcher and catcher skill. And so the better runner you are, you should have a longer lead distance. However, the difference between these columns is still like 1.5, 2.5. So that we found that the 2-foot rule, this recommendation is robust to player skill, whether it's a median or a 90th percentile or a 10th percentile.
I agree with this split for the number 2 option, because aren't a lot of those calls coming in from the dugout or from the catcher? They try to limit the number of decisions a pitcher has to make.
Yeah. I mean, to be fair, the pitchers, they've got a lot going on in their heads, and like their priority is the batter. Yeah. So they're not making optimal decisions on whether to do anything else. What we observe in the data is that their pickoff attempts are far more conservative than the model would generally recommend, where we would expect them to attempt like 10 to 15% of the time, whereas in practice we see them attempting like 5% of the time. They throw over it first.
Less of a focus on base runners in today's game.
Maybe justifiable though, given just like the limited mental bandwidth that you have. Okay. So project number 2 is about hitting, and this is a collaboration with Ron Yurko, who's one of the faculty fellows for CSDS over at Carnegie Mellon University. And this I mentioned that Reddit slide earlier was not my proudest moment as an academic, but the title of this paper is my proudest moment, Swinging Fast and Slow. That's a reference to Daniel Kahneman's Thinking Fast and Slow, which has had like a major influence in the way that Major League Baseball front offices think about the decisions that they make. So this problem was motivated by an experience that I had working with the Dodgers, where anytime a player like struck out with a runner on third in a big moment, my friends, when you work for a baseball team, you get a lot of like friends who like text you whenever something goes wrong. So let me show you what I mean. Okay, so this here is the 2020 World Series. This is game 4. Game 4 is famous for its ending, but prior to that, this is the top of the 7th inning. We're just getting started. We are trailing the Rays by 1 run.
Seager grounds a base hit into right.
Hey guys, is your tire pressure light stuck on even when your tires are fine? I had the same headache until I found this little genius. This TPMS reset tool is a total game changer. Just slap the patch on the sensor.
Here comes a 2-2 and a line drive base hit into left center. That will send Seager over to third. Digging for second is Turner, and he is safe with another extra base hit. Second and third, nobody out here in the seventh for LA.
Okay, so second and third, nobody out. That means that we don't need to have any more hits in order to bring these runners home, right? Like a deep fly ball will score the runner from third. Even like a ground ball in the infield might score a run. This would be like a time for a more contact-oriented approach rather than swinging for the fences.
Luke brings it. And a strikeout, one away. What a job. And Nick Anderson takes over. Great regular season, that bottom line. A little more. 0-2. On strikeout, 2 down.
So at this time, this was like during COVID, right? This is like October 2020. So I wasn't at the game. I was like with my coworkers at one of their apartments. And my phone was blowing up about how all hitters like need to have 2-strike approaches. They need to make contact in the situation. They can't swing for the fence. Incidentally, next batter was an intentional walk, and then Jock Peterson hit a single that brought in two runners home. Don't intentionally walk almost ever. It's not a good idea. So I want to first hide. And then pull this up. Okay, I'm learning. Now, whenever I got those messages, I was sort of agnostic to the answer because I don't know what's going on in the batter's head. I don't know if they are trying to swing for the fences. I don't know what they're doing. But in 2024, Major League Baseball released some new swing tracking data that allowed us to get at this for the first time. So they give us swing length and bat speed on every single swing. And so the first question that you might answer is, like, what's the relationship between bat speed and contact? When batters swing harder, do they make less contact? And the answer is actually the opposite. So this is like a naive analysis. Up here, I've got the distribution of bat speeds relative to the player's average when they make good contact. Down here, I've got the distribution of bat speeds relative to the player's average when they don't make good contact. And the distributions look really similar, but if anything, the good contact distributions are swinging actually a little bit faster than the player's average. So a naive analysis doesn't really answer this well. And you know, the reason here is that if the batter is fooled on the pitch, then they're going to slow down their bat in order to try to move the barrel to where they now think the pitch is going to be. Whereas if they guessed fastball and they were right, then they're going to keep swinging and they're going to swing hard. So it's not that they're swinging. It's not that because they're swinging faster, it's that they're making better contact, but rather there's this confounder. And there's another complication too, which is that when MLB reports bat speed and swing length, they do it at the point of contact. So for example, you might have two swings that are exactly the same, but if this swing is late, then the swing length is going to look shorter. And the early swing, the swing length is going to look longer because it's a later point in the swing when contact occurs. Similarly, bat speed will be less for this swing because the bat tends to accelerate as it comes through the strike zone. So I saw a lot of analysis once these data came out that were taking these measurements at face value, but we have to be more intentional about how we do that. So the approach that we took here is the first thing we're going to do is infer batter intention. So in particular, I want to know what does the batter's swing look like when they make solid contact. Our idea was if we want to know what the batter is trying to do, let's condition on the swings where they make good contact, and then infer from the bat speed and swing length on those swings what it was that they were trying to do. So in order to do this, it's like a Bayesian hierarchical model. We used a skew normal likelihood for the bat speed and swing length, which the statistics journal that we submitted to just ate that up. So that was why we did that. In this model, we have fixed effects for count and location, and then we have random effects for batter identity interacted by itself, and then also interacted with count and interacted with location. So what we learn from this is not only which batters tend to have faster or longer swings, but also how do batters differ in how their swing relates to count. So some batters are going to slow down their swing as strikes increase, and some batters are going to do it less. And that's what these results look like. On the x-axis, I'm showing you how much does the player shorten their swing as the number of strikes increases. So the scale is pretty small here. The range is like 3 inches per strike to 1 inch per strike. So it's pretty compressed. And then on the y-axis is how much does the player slow down their bat speed per strike. So the players up here, everyone is shortening and slowing their swing, because this is like the 0 line. So everyone's in this quadrant, everyone is slowing and shortening their swing a little bit as strikes increase, but some players are doing it more than others. The players here are making the smallest adjustments, and the players here are making the largest adjustments. I'll pause here for questions.
So might be a naive question. Does when they initiate the swing factor into this? Because I think based off the speed of the pitches, aren't they making decisions before the ball's even thrown?
Yes. Like when they start the swing, very much affects what we observe about the swing length and bat speed. Mm-hmm. And so by conditioning on good contact, we're trying to control for that. Mm-hmm. We're trying to say these must be swings on which the batter was on time, like their timing was good. And that's like the key idea of conditioning. Okay, well, feel free to interrupt if you have questions. Feel free to ask questions from earlier as well. We can go backward. But the key thing here is that there are differences between players in terms of how their swing metrics adapt to the count. And so the natural follow-up question is, what are the consequences of these differences? Would you rather be this player, or would you rather be this player? And so what we need to know is, if you swing shorter or slower with 2 strikes, does that cause you to make more contact with 2 strikes? And the way we set this up is as an instrumental variables regression, which it comes from econometrics literature. It's an approach to causal inference. It's not a very formal model, but we've got 2 separate models. We've got a logistic regression for whether the batter makes contact, and then we've got a linear regression for power. We use a metric called we use a standard metric in sabermetrics for measuring the power of a ball that was hit. Our instrument in the instrumental variables regression is the count, in particular the number of strikes, and the treatment effect for which we want to estimate the causal effect is this batter count random effect. So what I was showing you on the previous slide, every player has an approach that's reflected by these numbers, and so we're trying to understand what is the effect of the approach, of the different approaches that you can take. And we control for the difficulty of the pitch because we have a gradient boosting model that predicts the outcome of a pitch against an average pitcher. So we're controlling for the difficulty of the pitch that way. So the key idea of the instrumental variables regression is we are no longer looking at the variation from pitch to pitch in your bat speed and swing length, but we're saying, okay, so for the players who we observe them slowing down their swing more. For those players, what happens when they're in 2 strikes? Do they make more contact or less contact? And so in contrast with the naive results I showed you at the beginning of this section, we now get much more intuitive results. So this x-axis here is how much are you slowing down your bat speed with 2 strikes. This x-axis, which matches this one, it was the y-axis on the previous plot. This is how much are you slowing down your bat speed with 2 strikes. And the y-axis here is how much more contact are you making with 2 strikes relative to an average player. And in this plot, it's how much more power are you generating when you make contact with 2 strikes versus an average player. And so what we see is that players who slow down their swings more make more contact. And players who slow down their swings more have less power. So there's a trade-off here. And I'll pause again for questions. Okay, well, feel free to interrupt. We can go back to. Now that we've identified this trade-off, the question becomes, is the trade-off worthwhile? The slower bat speed is more contact, but it's less power. Is it worthwhile? Is it worth increasing your contact rate to decrease your power? And to answer this question, we set up a Markov chain model for a plate appearance where your state is the ball strike count that you're in. And the transition probabilities between states depend on your approach. It depends on how much you're slowing your bat as the number of strikes increases. Now, intuitively, this trade-off might make sense because early in a plate appearance, it's better to swing and miss than it is to make weak contact. Early in a plate appearance, if you make weak contact, then you're probably going to be out. Whereas if you swing and miss, you've got more chances. You've got 2 more strikes. Whereas once you've got 2 strikes, you would much rather make contact than swing and miss. Because if you swing and miss, you're definitely out. Whereas if you make weak contact, then at least there's a chance. At least there's a chance. So, within this Markov chain model, the value function is the linear weight of the plate appearance outcome. So in sabermetrics, we have a standard way of putting numbers on plate appearance outcomes, where a home run is worth 1.4 runs, a strikeout is worth -0.3 runs, and that's a standard thing that we're leveraging here. So the thing I'm going to show you next is the first plot I showed you that showed different approaches that batters can take. But now behind it, I'm going to put in like a gradient which describes the run value of that approach from the Markov chain model. And so it ranges from like red to blue, where red is good. Red is like an extra like 1 run per plate appearance over 500 plate appearances. Whereas the blue region is bad. That's like 2 runs. Your approach is costing you 2 runs relative to an average approach over 500 plate appearances. So the first thing I want to point out is this range is very small. Like it's a difference of like -2 to +1, a difference of like 3 runs on the extremes. It's a very small effect that we're measuring here, which is why I say that the trade-off is roughly balanced. Now, if you want to have a good approach in this region, this is someone who is making a big reduction on their swing length, but not a very big reduction on their bat speed. So you're shortening your swing without slowing it down, which is challenging because generally the way that you generate bat speed is with a big, long swing. I'll pause here for questions.
What metric did you guys use for power?
We used expected linear weight. Are you familiar with like xWOBA?
Yeah.
Yeah, so expected linear weight is just xWOBA, except that it's like, it doesn't have the weird WOBA scaling that xWOBA has. And then I just want to give you a taste of the last project I've got, which is on pitching. This was also Vicente, when I was with the Dodgers, he did a project with us. He was like a Rice undergraduate at the time, coincidentally, but he since went to work on in quantitative finance and made much more money than he can do in baseball or academia. But this was motivated by standard practice in baseball analytics these days is instead of evaluating pitchers based on the outcomes, through computer vision, we're able to observe the pitch that they made. So what do we care what the batter did if we know the pitch that was thrown, if we can fully measure that? It's pretty standard practice these days to apply like a supervised regression to predict the outcome of the pitch, and we use that as our evaluation of the pitcher instead of the actual outcome that occurs. Now, where that's less than optimal is with two pitches that I'm going to show you. So here's pitch number 1. So the key thing there is 104 miles per hour, but it's 2 feet off the plate. And then here's another pitch.
Playing a new position at left field this year versus center last year. Takes strike 3. And here's the thing with Yarborough.
So the second pitch, 88 miles per hour, but perfectly located. So they're both like 1-2 pitches. The first one results in a 2-2 count. The second one results in a strikeout. Okay, so the first question to think about is, which is the better pitch? And then the second question to think about is, which is the better pitcher? And these aren't necessarily the same. The 88 mile per hour pitch that's perfectly located, that's the better pitch. That's going to result in better outcomes. But if you could choose one of these two pitchers, suppose you didn't know the names of these pitchers, if I could choose one of those two pitchers, I'm choosing the guy who throws 104. Because the guy who throws 104, sometimes that ball is going to be in the strike zone. And the guy who throws 88 perfectly located, not all of his pitches are perfectly located. The velocity, like I know that's consistent. If you throw 104 this pitch, you're going to throw 104 the next pitch. But if you throw a perfect pitch right now, you're not going to necessarily throw a perfectly located pitch in the next opportunity. So so evaluating the pitch is not the same as evaluating the pitcher. In our gradient boosting model for predicting the outcome of a pitch, the most important variables are plate X and plate Z. That's the horizontal location and the vertical location of the pitch. Right? The most important feature of a pitch for predicting the outcome is like, where is it located? But those features are also the ones that tell you the least about the pitcher because it's highly variable from pitch to pitch, whereas velocity is really consistent from pitch to pitch. Velocity, movement, release point, these variables are really consistent from pitch to pitch, but they tell you the least about the outcome of the pitch. So, the standard approach I mentioned is to apply supervised learning and then to use the predictions from that supervised learning model to evaluate your pitcher. But in our case, we don't have like a new query point for which we need to make a prediction because we're not trying to predict the outcome of a pitch. We're trying to predict the outcomes that a pitcher is going to achieve. So in our setup, we've got these pitchers A, B, and C. We observe pitches from them, and then we need to make a prediction for pitcher A. We don't observe like a pitch trajectory. We only observe a pitcher, and we have to predict what the outcome is going to be. So instead of just fitting supervised learning model, the approach that we take is we need to estimate a distribution over pitch trajectories for each pitcher. And then once we have that distribution over pitch trajectories, then we integrate, so F hat here, that's our supervised learning function. That's our expected outcome of the pitch. We integrate that expectation with respect to the distribution of pitch locations. So it's sort of complicated to estimate this model because you're trying to estimate a distribution over 9 dimensions. That's the degrees of freedom that we observe in the pitch trajectory. And this 9-dimensional distribution, it depends on the identity of the batter. It depends on the count. We fit a Bayesian hierarchical model here with a 9-dimensional multivariate normal likelihood. And here is the outcome for a particular pitcher, Dylan Cease, who was with the White Sox at the time. What I want you to focus on here is the bottom left is where we think that Cease's pitches are going to be located in an 0-0 count. And then as we move up, the number of strikes increases. And so the distribution of locations is moving further away from the center of the strike zone. Whereas as we go left to right, the number of balls in the count is increasing. And so we've estimated that as the number of balls increases, Cease is going to locate his slider closer to the middle of the strike zone. And we don't have enough pitches from Cease in order to estimate each of these distributions separately. So there has to be some information sharing going on, where we sort of have to infer, well, other pitchers who throw sliders, like how do they adjust the locations based on the count? And what does that tell us about what Cease is likely to do? That gives us a prior for Cease, which we combine with the observed data to get like a posterior distribution over pitch distributions, not just location, which I'm showing you here, but all the 9 parameters: speed, release point, etc. And then the kicker here is that when we do this, the orange dots are our method. The green or gray dots are the standard descriptive model with some mean regression, so it's not totally naive. For the first like 300 pitches that we observe for a pitcher, if we observe fewer than 300, then we get big gains over the standard method that's used. Whereas those gains start to disappear once you have a big enough sample size, because then making optimal use of your data doesn't matter as much because you get pretty good estimates of what the players do. Okay. Sorry, I went through that a little bit quickly. This is the first time I've gotten through all 3 of those projects, and so I really appreciate you hanging in there with me. I went a little bit quicker to make that happen. But these are really just advertisements for some of the projects I've done. You can find information about all of these projects and more on my research page. That first one is on Archive. The second one is on Archive as well. The third one is not written yet. We've got some slides, but we still need to write that one and turn that into a paper. But thank you everyone for your attention this afternoon.
Any questions?
I've done some work with natural experiments and using them as kind of pre-posed. And I was going to ask about the rules changes, because I think we'd all agree there's been many rules changes, many of which baseball purists like myself probably don't agree with. But it looks to me like, but I didn't want to infer that your solution to most of those is to basically disaggregate by year and paying close attention to which years had the old rule, which has the new rules, or am I making that a little bit too simplistic?
Well, I showed you 2022 versus 2023 for comparison, although for the sake of the model, we're just using 2023 data, and we're not looking at the effect of the rule changes, but rather we're looking at within 2023, how do runner outcome probabilities change as lead distance changes?
I would assume that could be a pretty fruitful area of research for someone like you, particularly this year with an entirely new balls and strikes situation happening, which some people here might not know about. Like, there has to be some really interesting natural experiments to be able to look at.
And I'm not really well versed in like economics and like natural experiments, like what you need in order for that to be valid. But speaking of balls and strikes, a project that I really want to do is, I think that Major League Baseball could have a solution for their balls in play problem. So the problem is that in baseball, we're seeing more and more strikeouts, walks, and home runs, the so-called 3 true outcomes, because players have learned to optimize for these outcomes. But strikeouts and walks are boring. Fans like seeing balls in play. I think the solution, now that they can automate the strike zone, I think the solution is about changing the shape of the strike zone in a way that you couldn't do it when you were entirely reliant on human umpires. I think that if you made the strike zone shorter and wider, you would get more balls in play, fewer strikeouts and walking. That has to do with like the placement of the bat. Bats tend to be horizontal. And so if you make a vertical miss, that's a swing and miss. If you make a horizontal miss, that's weak contact. So that's one of the projects that I've got on my burning questions list.
We have a question online from Aichuan Xin, who says they do research with MLB data and analysis. He's going to SABR conference and would like to meet up and discuss.
Great. I'm not going to be at Saber Analytics, which is the one in Phoenix in March. It's a good conference. A conference I like even more is Saber Seminar. which is in Chicago in August. So I'll be at Sabre Seminar this year. I won't be at Sabre Analytics this year. But those are two great conferences if you're interested in baseball research to present at and to attend to see the latest news.
If people were interested in getting in touch with you, your Rice email address would be a good way.
Yep, scott.powers@rice.edu.
Getting back to the rule changes this year, how do you think, just in your expertise, the challenge system is going to impact the game?
I think you'll have fewer really frustrated fans because in like the really outrageous calls, like we'll get those right, and so I think that'll assuage some of those concerns. I don't think it's going to be like a huge impact on like who's winning games or not, because I don't think it's like a great number of those calls that are having outsized outcomes on games. I do think that there's a lot of interesting research opportunities there with like selfishness and like self-judgment, right? Just like when is the player deciding to use, because you're limited to I think 3 challenges, and so how does the player decide whether to challenge this pitch, which was close, versus saving their challenges for their teammates to challenge ball strike calls? I'm very curious to see how that plays out, and maybe some fun projects to be done there.
Yeah, there's a rumor some people are talking about that they've already decided they're going to get rid of the strike zone graphic because technically the rule is it can't come from the dugout, and I don't see that. To me is going to be a huge that's an implementation issue, but how they're going to regulate that when everything in today's game like comes from the dugout.
How do you feel about the strike zone graphic? Do you think it's a good thing or a bad thing on broadcast? Like your personal experience.
Yeah, when I don't have it, I really miss it.
I do too.
Yeah, when there's games on certain networks, I'm like, where's my strike zone? Because that's when I'm watching baseball, like I'm locked in. I want to see what's going on, and when it's missing, it's like, it's difficult. Sometimes difficult to tell whether it's a strike or not. So I'd rather have more information than less.
Although you might feel less rage in your heart if you didn't see the strike zone there and have that confirmation that it was in fact the ball.
Well, what's baseball without the rage?
I think it's going to be an interesting dynamic between the dugout that's not supposed to be involved whatsoever, and I just don't think that's realistic. I mean, if you have Yadier Molina behind the plate, yeah, I mean, he can make those calls, but not every catcher is the Hall of Fame caliber and going to be able. And then, and so much in today's game takes out of the players, but they're trying to put it back with basically saying the catcher and the batter and the pitcher are the only people that can make these challenges. I just don't. It's going to be. I think there's going to be some fits and starts in the implementation.
And I think the rules about video usage should prohibit them from having like the video broadcast in the dugout. And so the technology restrictions should stop teams from like having that communication, but there are always trash cans in the dugout that can be used for that.
I didn't say it.
There seems to be a psychological component to especially the swinging and the first project with the force outs. That I guess in education you would call it learned helplessness, is where earlier mistakes make it more likely that future mistakes are going to happen. How do you account for that in these types of statistical models?
Could you explain the learned helplessness? I didn't.
Yes, and so in education, there's a phenomenon, learned helplessness, where a student who fails at, let's say, task 1 and task 2 is more likely to fail at task 3 because of shock confidence.
They're not independent outcomes.
Yeah, that's earlier mistakes psychologically weigh down their thinking process, or even the perception of mistakes can do that. But like you said, these are people; they're not always acting optimally. So, how do you include those types of psychological aspects in things?
I'll be honest. This is an area that's pretty underexplored in baseball analytics, and I think it has to do with it's a signal to noise ratio question, where when you're trying to model outcomes where you can actually like observe tangible performance, then you're just going to have like greater signal in your model. Whereas like the less observable in this case the mental performance is, like the lower the signal to noise ratio is going to be. And I think that's why it hasn't been as explored as much.
Any other questions? Thank you so much.
Have a good time.